halides, we've talked about alkenes, we've talked about alkynes. We haven't gone through a lot of their chemistry, but we've seen a little bit. Okay, other things that you may have heard of, we've kind of mentioned in class, they came up in lab a little bit, is if you have an OH coming off of a carbon, that's known as an alcohol. So what we think of as alcohol, like the drink, is ethanol or ethyl alcohol, which is two carbons, ethyl, two carbons with an OH attached to it. And so that gives us what we think of as like our drinking alcohol. But methanol is another example of that, methyl alcohol, which is sometimes used in fuels or as solvents, isopropyl alcohol, rubbing alcohol. And then this little group, this little OH, is really important in biological systems. All carbohydrates are made from lots and lots of those. So that's what kind of makes up the chemistry of sugars and carbohydrates.
Wait, carbohydrates made out of what?
Well, they're made out of carbon with OHs coming off of like every carbon. All right. So what?
Is that considered an alcohol?
They're all alcohols, yeah. Yeah, from a chemistry standpoint. Yep, anything with an OH. Now, when you have molecules with different functional groups on them, it's not that simple because like this functional group does one thing, this functional group does something else. So you might name it one or the other, depending, because it really has both. So sometimes they're combined, like something with an alkene and an alcohol might be called an enol if they're close to each other in a particular place. So anyway, there's lots of variations. Oh, I should mention, there are specific sugars called sugar alcohols. I don't know if anybody's heard of them. They have names like xylitol, mannitol, sorbitol. They're in a lot of gum and like that kind of stuff, like sugar-free gum. They're when a sugar molecule had some reaction, has some chemistry done to it to give it some more of these in place of some other stuff, and that makes it not digested. So that's why those have warnings on them sometimes. If you get like sugar-free candy, I don't know if anybody's ever noticed that. Sugar-free candy usually has some sort of warning that says like, don't eat too much and poop yourself, or something in slightly more delicate terms than that. But that's basically what is happening, that these sugar alcohols are kind of just running through you and they sort of push everything out as they go, sometimes in a way that you cannot control. So don't eat an entire bag of sugar-free candy is, I guess, the lesson. Really don't eat a whole bag of any kind of candy, but. Okay. The next group is all things based on a carbon double bond oxygen, which is called a carbonyl group. So depending on what else is connected to that carbonyl group, you can have one of a number of different compounds. So these are all based on the carbonyl group. If you have a carbonyl group with an H on one side, you have something called an aldehyde. Like formaldehyde, acetaldehyde. Aldehydes smell very strongly. They're also somewhat reactive, or they can be. If you instead have carbon on both sides of that carbonyl group, you have what's called a ketone. Ketones are important functional groups in the body for pretty much anything that ends in -one. So like hormones are all based on ketone functional groups. If you think of all those molecules that end in -one, those are going to be based on ketone groups. Ketones and aldehydes also are important in sugar chemistry. So you'll see some sugars based on aldehydes, which are known as aldoses, sugars based on ketones, known as ketoses. And if you're diabetic, you can have some, I don't know if you've heard of this, you can like smell ketones coming off of somebody's breath if they're having really, really low blood sugar. And that's because of what's happening to the sugars in the body based on this functional group. Those kind of smell also. When that you've probably smelled, what we've used in lab, acetone is a small ketone of just 3 carbons, and it kind of has that real, I don't know how to describe it, like a solventy smell, like nail polish remover or something. If there is an OH on one side, so you've got a carbonyl group and an alcohol together, that's known as a carboxylic acid. So that's organic acids. That's things like acetic acid, which we've used, which is vinegar. But there's lots of other ones, benzoic acid. This is important in sugar chemistry as well. Not benzoic acid, but some of the amino acids that end in acid, amino acid itself, all those have this type of a functional group on them. And then some of them have other extra ones like aspartic acid. If you have O and then some other carbon stuff instead of a hydrogen, that's known as an ester. Esters are one of our biggest functional groups in terms of flavor and fragrance chemistry. So a lot of esters have really distinct smells. If you think about things like the smell of vanilla or mint or citrus smells, most flower smells, those are all based on esters. And then the last carbonyl one that we're going to look at is when there's nitrogen connected to it. And that's known as an amide or amide. Amide is also known in biology as a peptide. This is the functional group by which amino acids link together. So the carbonyl comes from the acid side, and the N comes from the amino side, because amino means nitrogen. Those hook together, and you have what's called a peptide bond, and that's how proteins are built. Amino acids hooking together in that particular way. So proteins will have lots and lots and lots of those in them. Also, polymer chemistry is important in these two. Ester, when an ester is on like 2 sides of a molecule, so it keeps continuing and making a big chain, that's called a polyester. So like polyester, the fabric. And then polyamide is also, that one's not as well known, but polyamides are another name for nylon. If you've heard of like nylon fibers, or what else is, some of the like really, really strong fibers like bulletproof stuff, Kevlar and Nomex, those kinds of materials are also polyamides. All right, so those are the carbonyls. And then the last couple we'll look at, non-carbonyls. SH are called thiols. Those are the stinky ones. Thiols are responsible for a lot of really bad smells. And then if you have nitrogen without the carbonyl next to it, those are known as amines. And so those are things like amino acids. They're also in bases. They also have some bad smells. Things like decomposition products are often made of those kinds of things, like when you're decomposing fish and things like that. Definitely have those things. Thiols are from bacterial activity, so like farts and that kind of thing is thiols. There are some that are just like ridiculously, almost dangerously pungent. I had a professor in college who had a note card where 1 drop of a thiol compound had spilled on it 30 years earlier, and you could still like smell it really strongly, which is pretty amazing, because you know the number of actual molecules in there was not huge, because it's been evaporating for 30 years. So it means like every single molecule just hits your sensors. And yeah. So let's see, did I forget? I mean, I definitely forgot some. Not like, I guess not forgot. I left some out, but I think these are the main ones that we can work with. I guess let's look at one more, as long as we've got a little room in the bottom here. We don't really, but. If you have an O in between two C's, that's known as an ether. There's one particularly famous ether, diethyl ether, which is sometimes just called ether. It's a solvent. We use it in organic chemistry all the time. It's really low boiling, super volatile. And for a long time, it was used as an anesthetic. Like you could, because it's so volatile, you would like have somebody breathe it in and then they would kind of fall asleep. It's a really terrible anesthetic because you can't control it very well in terms of how much someone's getting. It is deadly. So if they accidentally breathe in a little too much, they just die. And you come out of it, it kind of acts like drinking alcohol, but like really, really strong. So you have this really terrible, like, yeah, it's like unimaginably horrible hangover, I guess, when you come out of it. Some people do use ether as like a recreational drug. It's not a great idea.
There's a movie, Fear and Loathing in Las Vegas, where they go and they're going to go to the casino and they like start sniffing it out of a handkerchief.
Mm-hmm. Yeah. Yeah, not a great idea. It's also super flammable because it's so volatile. So there's a lot of stories of like old, it wasn't that long ago that people would smoke in lab while they did, like students would just be smoking in lab while we did chemistry. And so every once in a while, somebody would like open up a bottle of ether and somebody would light up on the other side of the room and some fire would just kind of shoot through the room through the ether vapors. And I was just like, oops, forgot, sorry, I didn't realize you were smoking there. So, yeah. What? Because everybody smoked all the time. Yeah. I'm like just old enough to remember like being on planes where people were smoking, which is not great. Because if the smoking section on the plane is like, I think it was either the front or I think it was the back, but like it's a plane. So it's not like it's gonna make that much difference. All right, so let's talk about how we use this. The main thing I want you to be able to do now, if you go on and take organic chemistry, you'll kind of look at the chemistry of all these different groups and how they connect to each other and all the cool molecules you can build from functional groups. One thing I want you to be able to do is identify the functional groups given a table. So again, you don't have to memorize this in the next week. You got enough to do, but be able to identify that. So let's look at some interesting molecules and find some functional groups. So anybody have a favorite molecule? Something you can think of? Some medication or acetaminophen, all right. Look at the structure. Can you see a picture of it? Yeah, here we go. So let me pull this in. Okay, so let's take a look at that molecule. That's acetaminophen, aka Tylenol. What? Well, depending on how you define bad for you, but yeah. Yeah, acetaminophen has a really relatively low, like dangerous dose level, which people exceed fairly regularly without really realizing it. You know how like it says in the bottle, don't take more than 2 pills every 4 hours, and then don't take more than 6 in 24 hours. If you take more than 6 in 24 hours for acetaminophen, you're like seriously in danger of, or your liver can be in serious danger. And a lot of people just kind of take that as like a guideline instead of don't take that much. But acetaminophen is a useful pain reliever, especially for people who can't handle other types of anti-inflammatories like non-steroidal like Advil and stuff like that. If you have stomach problems, you have kidney problems, you can't take those, and so this is your best shot. So what are the functional groups in acetaminophen? So first, what do you look for when you're looking for functional groups mainly? Yeah, like in general, if you're looking at a molecule and you want to find the functional groups, what are you looking for? Yeah, so you're looking at non-carbon stuff, basically. Like where are and this structure has it nicely highlighted in green and yellow, or green and red. that there are some pretty clear functional group areas. So the trick in finding functional groups, like what's this? We see one down here, right? Anybody remember what that one's called from before? What type of a functional group is that? That's an alcohol functional group. Yep. And so then above, we have kind of a choice to make, because we've got a carbonyl, which is the C double bond to oxygen, and then we've got this nitrogen next to it. So one thing that I see people make mistakes on these, even when there is a chart here, is kind of not noticing that those things mean something together. So you can't just call the nitrogen an amine, and you can't just call the CO a ketone. You have to notice that those things are together, and that functional group is best called an amide, because it's the carbonyl group with the nitrogen right next to it.
I think it's confusing though, because they put the amino in the name, and then I was just looking at the end.
Mm-hmm.
Amine made amino acids.
Right. It is confusing. So you should write to them. I'm not sure who it is. Whoever named this. But we're going to call that an amide or amide functional group. And so that's the functional groups in acetaminophen. All right. Let's look at something bigger. Anybody got another favorite? Meth? That one I know. All right, before I look at the structure, anybody want to guess what types of things we might see in that structure based on its name? And again, we might be wrong.
An amine.
Maybe an amine, because that's how it ends. Yep. And maybe like a methyl, maybe a methyl something. How to make, yeah. Let's see how many like questionable searches we can make in this room before somebody comes in. What's happening in here? Oh, I'm signed in under my name too, so that's great. Yeah, so this is it here. Really small molecule. Right. And we've really just got the one main functional group here, which in this case is an amine because it doesn't have that carbon next to it. So the meth amphetamine part, the meth comes from this CH3 right here. So there's a methyl group on the amine, on the nitrogen. I don't know what the amphet part is for. That must be the rest of this molecule. The other thing we could talk about that is not exactly a functional group, but sometimes is named as such, is that these both have aromatic rings. In this case, specifically, they're benzene. So those are sometimes called an aromatic functional group. And you'll see a lot of these things that we look up have stuff like that. The meth comes from this specifically this methyl that's connected to the amine. Let's see. Let's look at a big antibiotic. Anesthesia molecules are small because they are volatile, but we could look at that too. Do you have a favorite anesthetic? No.
I have one that looks kind of big.
Okay. Okay, yeah. Thorzine's like a pretty serious
It's like they use it at my work.
antipsychotic, right?
Yeah.
It's one of your favorites, huh?
I was doing mental health.
I heard that somehow you popped up on my Facebook feed that I might know you. I'm like, yeah. I'm like, how does that even happen? It's so weird.
Okay, so once again, we've got, so this one is Thorazine. Thorazine is the brand name, right?
Yeah, it's like little, I don't know what it's called.
I saw it over here. Chlorpromazine is the generic. So what do we see here? Yeah, we've got actually two amines. It isn't quite because it doesn't have an H on it, so it's a little bit different. It's also in a ring, so it's called a I think it's something like a thioazelactam. So we didn't get into that. We'll just skip that one for now. And then we've got our halide or halogen, and then our two aromatic parts too. Like that. Lactam. These rings so rings that have non-carbon atoms in them are called heterocycles, and those all have different kinds of names. I don't remember that one specifically. But I want to say it's thorazolactam or something like that. Maybe we can get it here. Morpholine, thiomorpholine, right? So we didn't talk about that one, but that's what that is. Some big antibiotics known as macrolides, like zithromycin.
With the Z-Pack.
Yeah, that's the Z-Pack. Let's see. We'll just assume Wikipedia has the right structure. We may be way off on that one.
Can you try to name that?
No,
No.
let's not.
Would someone even name something like that?
Yeah, you use the software to do it.
Okay.
Because you can, I mean, if you follow the rules, which we didn't even learn like all the, because there's different kinds of rules for all these different kinds of things. But if you follow the rules, you could do it. In fact, it's probably in the Wikipedia that what its IUPAC name is. Maybe not.
Might have been under like the synonyms. Or, yeah.
Here, we can look it up in the CAS. Here you go.
Good God. That paragraph is the name?
Yeah, that is the name. You could also name it in those ways. So yeah, it can be done. This is kind of a cool antibiotic. It's really widely prescribed and it's really misprescribed. Anybody know why? Like, what's so special about it?
He's only take it 5 times.
Yeah, like the biggest problem with antibiotics is patient compliance, because they give you a run of like 10 days and you have to take it 3 times a day for 10 days. And a lot of people take it for 3 days and go like, nah, I'm fine. I'm not gonna take it anymore. And that breeds really dangerous antibiotic resistance. So what? Yeah, it's really, really, really bad. So with this, you take like a bunch the first day, and then you kind of take one for a couple more days, and then you're done. And it stays in your system and just works for that full period. So they have a lot better patient compliance that way, because you don't have to remember to take it 3 times a day for 10 days, even when you're healthy. The problem with that is then it becomes more prescribed. So this is really overprescribed. It's because it's indicated for respiratory infections. So like if you have really bad pneumonia or something, you might use this. But 90% of respiratory infections are viral and don't indicate for antibiotics. So a lot of times, like when you have a bad cough and you go to the doctor, they're like, take a Z-Pack and see if you feel better. But really, you almost certainly do not need those antibiotics.
I used to get like sinus infections constantly, and they would just give me the Z-Pack, and then finally my doctor was like, you can't take the Z-Pack ever again. They will not prescribe it to me anymore.
Yeah, you probably are breeding resistant bacteria to it now, because it didn't kill them off and it just kept coming back. All right, so let's look at some functional groups here. This is a big molecule. It's got a few different ones. So what do you think? Who sees a functional group? Not color-coded either, so you have to actually look for it.
Alcohol.
Alcohol, yeah. So there are 1, 2, 3, 4, 5 alcohols in the structure. An amide, yeah, where do you see an amide? Oh, actually, this one is an amine because it doesn't have that C double bond O next to it. So that's with the N, amine.
Is there an ester there?
Yeah, there's an ester, which is the carbonyl with the oxygen next to it. There's another amine over here.
So would it always be like one of these other carbonyls, or would it ever just be a carbonyl?
It would never just be a carbonyl.
Okay.
It's always one of the other ones.
Is there ether?
There is. There's one ether, and then there's some that kind of look like ether. So this is a true ether. When it's an ether on a sugar molecule, which is what that ring thing is, it's known as a glycoside, but it's the same thing. And then these other ones are a little different because of their position in the ring, but we can think of them as ethers from our standpoint. They're actually called acetal. It's like 2 oxygens on 1 carbon that then go off to other stuff. But that was on our list. So. Yeah, it's a lot of stuff going on there. Epinephrine. Okay, so we can look at that one. It's a molecule. What do you see there? Alcohol. 3 of them, right? And amine. Yep. Alcohols and amines. Other interesting thing that you see on a lot of these drug structures. So this one, you know, we talked about the dash or the wedge bond. In this structure, those are 2 different, or in this molecule, those are 2 different structures. You can try to think about it in your head if you want, or you can just take my word for it, that if that OH were on a dash, that would make a different molecule. And in this case, as is true with a lot of drugs, only one of the 2 is active, is bioactive. Sometimes the other one is dangerous. Sometimes the other one is just not active at all. Depending on that, they have to design the molecule in one way or another. And that's because a lot of those things in our body have that kind of asymmetry to it, like our amino acids and our sugars. So only one of the 2 possible ones will work, and it has to be specified which one is actually working. I don't know for this molecule if the other one is just less effective or if it's dangerous. Sometimes that's an issue. All right, more, or you think you're good? What? Isn't that a enzyme? Oh no.
It's a neurotransmitter.
All right, so what do you see in that one? Careful. That O with the 2 carbons kind of looks like an ether, but we have to look at what it's next to, because it's really an ester because of the carbonyl group next to it. Yeah, this is a little bit different because it's an amine, but it has a 4th thing, so it's charged. So that's an ammonium, like ammonium ion. But yeah, same idea.
Okay.
So make sure when you look at one of these groups, you also look at what's around it, because sometimes that change, because if you just looked at this O, you'd say, oh, it's an ether. But if you look at it together, you see that it has the carbonyl next to it, and it's an ester. All right. That's all I got. What else do you want to talk about?
Are there any other interesting molecules?
Oh, there's so many interesting molecules.
Well, one that we should be like familiar with, like that, we might use or come in contact with on a daily basis.
Well, it depends on what you do on a daily basis. Well, okay, let's look at opiates.
From a daily basis.
I don't know your life, Let's I guess we could just look at morphine. So this has a really cool structure because what's happening here, we haven't really seen anything like this so far in this class. But what you have is what's called a bicyclic compound. So bicyclic can just mean rings hooked together, like all these are here. See these rings kind of all hooked together? But then there's an extra ring that comes out this way. So you kind of have to go into the third dimension to see this structure, because there's another 6-membered ring with a nitrogen in it that comes out kind of orthogonal to the other rings. And this particular structure is the basis for that entire thing. The whole like human relationship with opioids comes from that really unusual structure. And it actually took a really long time for organic chemists to figure out how to synthesize this type of a molecule and how to really make it. And some pretty clever chemistry went into figuring out how to get that thing to connect, because it has to connect in just the right way, going just the right direction. So you look at these dashes and wedges. So this thing's coming out at you. The hydrogen's coming out there. The hydrogen's coming out there, and the OH here is going back. If those switch around, you have something different. So it has to be just in that specific particular way. Yeah.
If it's like so small, and how do they know? Like, how do they figure out what it looks like?
We use analytical techniques up in lab, which we didn't get to do a whole lot of this semester, but there's a powerful one called NMR, nuclear magnetic resonance, which is related to MRI, where you can look at where the hydrogen molecules are, and you can make some conclusions based on that. When you're talking about three-dimensional structure, there's really only one tool that we can use, and that's X-ray crystallography. You can make a crystal of something, you can shoot X-rays at it, and from the way the X-rays diffract through the molecule, you can do, well, computers can calculate, kind of back calculate and figure out what the structure must have been to cause that pattern to occur when the X-rays pass through it. So that's how, through a lot of analytical techniques, and just a lot of like, so you know what molecules you start with, you do a reaction, you think you know maybe what happens, so you can kind of at least guess, and then see if the spectroscopy confirms your guess, like the analysis confirms your guess. There's a whole field of chemistry where people just like extract new molecules from sea cucumbers and like all kinds of other weird stuff in the rainforest, and just try to figure out what they get, like what kind of molecules they get. So they're just starting from nothing, trying to determine the structure of a molecule, which is very difficult. There's a lot of tools that help us do that. That's how most drug development, I don't know about most, that's how a lot of drug development starts, is people just discover weird molecules that some organism has evolved to make that happens to protect it against some other kind of weird organism or cancer or whatever. And then we start testing it in the lab, and we start tweaking it with organic chemistry, putting a methyl group here, an OH there, or whatever, and trying to figure out what does the best job.
It seems to be really hard to go to the molecular level and just pick out one strand of a methyl or an ethyl.
Mm-hmm.
Right,
It
so
is.
how would you synthesize a compound?
Yeah.
All right,
Are they
let's
able
look
to-
at it.
Are they able to do it so precisely?
Total synthesis is the name for like starting from a small molecule and then synthesizing it. So here's somebody's presentation. I hope they're right. I don't know if they are. So you've got more. This is another kind of neat three-dimensional view of this, by the way. Same structure, but you can take opium, and that contains some of these, and you can separate them and then adjust their chemistry accordingly. Like morphine and codeine are very, very similar. They only differ by this. This is shorthand for methyl group. So instead of writing CH3, they wrote OME. So it's the exact same structure, except you have either an alcohol here or you have an ether, a methyl ether there, and that gives you the difference in those two compounds. All right, so let's look at, this is the biosynthesis, so this is how the plants make it. They start with tyrosine, which is an amino acid, combine it with dopamine, which is why it, or partially how it acts to kind of mess with your neurotransmitters like that, and kind of put this stuff together through enzymatic actions. And then here is this kind of classic synthesis from the 50s. They start with this molecule, and each one of these is a separate reactive step. So like you put in this thing, you mix it, you let it react for a certain amount of time, you stop, you extract it, you receive the product, you move on to the next step. So by those first 4 steps, you've lost you only have 56% of what you started with, and what you've done is you've put this BZ, which is a carbon and then a benzene ring, and then you've added these things over here. Then 2 more steps, you lose some more, you get some methyl groups on there. So you had to do all of that just to kind of put something there, because that was hard to do. This thing is called a protecting group. So what you've done is you put that on there to stop it from reacting with other things, so you can mess with the other side. Then you got that thing on there, you can deprotect that, and then mess with that side and get to there. So you basically did the same thing to both sides. Then you gotta do this other stuff to put these things on there. Once you got that, then you can do this thing, this other type of reaction that called a Diels-Alder reaction that makes that 3rd ring. And that makes, because you put this thing here before, you can now connect it over on this side and make that weird 3-dimensional thing coming out. A few more steps, and you've made it to your product in a whole whopping 7% yield. So if you started with 100 grams of starting material, you would end with 7 grams in the absolute best case scenario, which is the yields that are always reported. So, and think about, like, each one of these is basically at least a lab period, right? Probably more, because a lot of these reactions take 8 hours or 12 hours or something. So you're talking about working on this for a really long time. And somebody had to kind of work out each of these reactions too, and actually get them to work and find the right conditions. So you're talking about years of work to develop a synthesis like this.
Once they like develop this, are they able to like add catalysts to certain steps to make it go faster?
Sometimes. So what would happen is somebody would publish this, so like Gates published this in 50 something, 52, I think it said. And so then if like, let's say a pharmaceutical company wants to license this, then they want to make it, they probably don't want to do that because it's so many steps, it's so long, it's probably a lot of dangerous stuff in there too. So then they're going to have all their chemists try to optimize it or come up with a different way to do it that's more efficient. Depending on how important a particular molecule is, more people may be working on trying to make the more efficient synthesis, or do it in what's called green chemistry, where you try to do it with less hazardous waste, less hazardous materials, less like throwing stuff out. But yeah, so that's how that works. And like that little molecule's relationship with the receptors in our brain has, as we know, caused a lot of trouble over the years. Continues to cause a lot of trouble. And a lot of molecules have neat stories like that too. Do you have a question?
Well, I was gonna say, like, likewise, it's done good for us too.
Sure. Yep. Yep. Control pain and such. Good place to stop. I don't know. Other things you want to talk about? So we'll have, I don't know if you've started kind of going back and reviewing for Wednesday, but probably the best thing to do that I always recommend is get your book out, get your old exams out, and just randomly flip some questions here and there and see if you can just do them with no help, with no looking back at the sections. Just get yourself some different problems and try to do them. Because chances are you remember a good bit of what we've done so far. Like you can do those questions again. And so it's not worth spending your time like reading through every chapter that we've gone through so far, because a lot of that stuff you've got. So test yourself, and the ones that you're getting wrong, the ones that you're not finding the right answer to, that's make a mark of that, make a note of what type of a question that is. Those are the sections you want to focus on, the review stuff that you want to work on. If you do that carefully, you should have a pretty good list of, okay, here are the things that I'm definitely not getting right and that I'm struggling on, and those are the things you can focus on in the next few days. Yeah.
What was the sections that we went over, like that wasn't on the last exam?
Nothing. Well, yeah. Sorry, that's not true.
11.
So yeah, it would be those last two sections in 11. I think 11.5 and 11.6. I still have the book up here. 11.7 and 11.8 were the ones that we didn't do, and then what we did today about functional groups. It's not exactly. they kind of, in this edition of the book, they kind of spread it out because they talk about different functional groups in different chapters.
Okay.
So it's probably best to just stick with what we have on the notes as an
Okay.
overall review.
The final exam is the same tab as our other exams?
No, it's because we have so much less time, it's gonna be all multiple choice. So I'm not sure how many questions exactly. I'm guessing it'll be something like 40 or 45 questions of multiple choice.
And you're gonna post it on Blackboard, not like that, because I never even became part of that like journal thing that you guys had going.
No, I'll post on Blackboard yeah. Yeah, and let me know when as you're studying, if you run into stuff, to trouble this week. If you want to come by, I should be in office hours, Wednesday and Friday, Thursday. Next week, I will be here early before our exam, but not like in the middle of the day. I'll probably be here around 4:30 if you have last minute questions on Monday. Certainly email me or send me messages through Slack if you have questions. Or come see me, and happy studying. Oh yeah, and of course Wednesday we'll have time in class, so if you can get studying done in the next couple days and come to class with questions on Wednesday, that would be a good time to.
Yeah, so this Wednesday is just
Look
check
at
out.
Yep. And a quiz, like a review quiz on everything.
Oh, yeah, you sort of do that all together.